Mr. Layton lays it out on the line, all the problem sets are a lot easier that I've found, are a lot easier that way. It really simplifies everything. Because I tried writing it down and everything, and I can get it, but it's just so much faster and simpler if you put it on a problem line. Would that be what you call it?
Basically, you just put it on a big fraction.
Well, yeah, if you're talking about
big fraction, essentially.
Yeah, strategies for doing problems. There is kind of the step-by-step that, Tim Chester's been doing, and I think that's typically the way that, we've been taught to work through problems. Once you start getting into, the engineering disciplines, and you can put it on that one single line and sort of, knock it out in one fell swoop. But I recommend for now trying to do just using both. You don't have to necessarily pick one. And what I find is a lot of times some problems lend themselves to one technique and some to the other. So there's no perfect solution, literally. Okay, let's take a look at the syllabus so everybody's on the same page with that. And then we'll get into chapter 7. So week 6 is behind us. And just cruising down here. So we've taken exam 3. I did extend that deadline to Friday evening. If you have specific questions, you want to ask me about specific questions, I'm happy to answer them over email, and then I'll post it to the class so everybody sees the answer. Because typically there are 1 or 2, 3 or 4 questions like, oh, we didn't cover that in class, or oh, it wasn't in the book, and typically I can justify saying, well, we covered something similar, you should have been able to infer, but the course does change subtly from year to year. It's not the same exact course every year, and it could have been that I had a particular topic that I thought was relevant in a previous year that was perhaps skipped over or not as relevant this year. So I'm glad you're curious about it, though, because it'd be great if everybody got a perfect score on every test. Okay, so exam 3, problem set 1 is due this Thursday, late a week from Tuesday. Problem set 1. Questions on that?
You need to do before next Tuesday.
It's due before next Tuesday. So it is the window of opportunity for submission starts in 2 days, and it closes in 7. Yeah. Well, it's like paying your bill. I mean, your credit card doesn't say you have to pay it right now. I mean, they say it's now due, and then it eventually becomes overdue. So yeah. And then week 8 will be chapters 7 and 8. I'm going to go over chapter 7 today. I'm going to let Tim do chapter 8 next week because I will be in Washington, D.C. for my National Science Foundation grant. What I'd like to say about chapters 7 and 8 is that chapter 7 is more the science, and chapter 8 is more the technology, if you will. And if you remember, we've kind of had that discussion about the fundamental difference between science and technology. Science is more or less the discovery of nature, measuring, observing, testing, hypothesizing, etc., about what the laws of nature are, what things are out there to be discovered. Technology is more the exploitation of those discoveries. So, look, we drilled into the ground, we found some oil, we explored, we then sent that oil off to a lab, we found out what the chemical constituents are, we set it on fire, we determined how much energy is from it. That's the science. Now the technology is, what can we do with that? How can we harness that fire? Well, we can build cars, we can build heaters, we can build, our technology. So in a lot of ways, and that's kind of how the book is structured. You've got a science chapter and then a technology chapter. As I mentioned, I tend to prefer the even chapters, which are more the technology chapters, but I'll let Tim have fun with that next week, so we'll just go over chapter 7 today. All right, so as usual, I'm going to hit the high points of the figures. That seems to be the most effective use of my time here in lecture. So I'll get through as much as I can. Let's see, how many sections are there in chapter 7? Looks like there are 13 sections total, including the summary. Chapter 7 starts on page 213 and goes through 277, so there's 60 pages or so in the chapter. Yeah, it's a pretty beefy one, but it goes pretty quick. Okay. Well, and I really can't say enough nice things about these authors. I feel like the ideas, once in a while you'll hear a little bit of bias in their voices, a little bit of, rebuking the fossil fuels industries for being, not the environmental stewards that we think they should be, not being as forthcoming with some of their information. But on the other hand, they have a commodity, they've invested time and money to get access to those resources, and they're hoping to get that back. But what I do like about these authors is the data and the figures that they show really allow anybody who cares to look at it access, into the quantitative nature of this, so that we're not lying, cheating, stealing, killing, etc. So that's what I really like about this book in general. All right, so let's hop into chapter 7. And we've got, 34 figures or so and a few boxes that aren't shown, but let's just get right with it. So what we're looking at here is the cross-section, if you will, of oil reserves. So again, you probably remember there are 3 phases of matter: solid, liquid, and gas. And what we're primarily focusing on here are the oil and gas. And so again, all of these are going to be some kind of hydrocarbon. We'll get into the chemistry here when we get a little bit later. But obviously, less dense substances rise and more dense substances fall. So you've probably all seen an oil slick on the top of water. So this is just natural physics in action, with the less dense oil rising to the top of these water reservoirs. The gas obviously is on top of that. The reason this little bubble is formed is that it's sort of stuck beneath a big layer of rock. And obviously the sources of the oil and gas are from those photons that we've talked about before, hitting the earth, doing photosynthesis, and now they're buried, and they're there as an energy reserve. So this is just sort of one way for oil and gas to be trapped under other layers of rock that have been laid down over the eons. And this little buckling that's occurring right here, this is just 2 plates that might be coming together that haven't quite fractured. They're just sort of buckling, if you will, and made a nice little natural cap here. Another way for these different phases of matter to be segregated is through a fault line, where in fact the earth has indeed sheared. And so rather than this oil being able to sort of slosh around under this cap rock, it's sort of tucked away in a little pocket instead. And this is what the oil companies are going after when they start doing their surveying and drilling. Another way too is for a salt dome to form. So this is something that's crystallizing down as salt is coming out of solution with the surrounding water. And again, you sort of have the liquids being trapped more or less by the interface between the 2 solids.
Is oil always on top of water?
Oil is always going to be on top of water, yeah. And this is in the case of this, the light crude and even some of the heavier crudes. The tar sands oil, if you remember, it's much more mixed in. So it hasn't really done a full phase separation like you see here. So it's there, but not in a pure liquid form. But given enough time, enough heat, enough pressure, and that's really what's going on. You can sort of think of this thing cooking in the same way that when you make your gravy, if you will, from baking a chicken, all those fats come to the top of that liquid. Same exact physics going on here. All right, so cruising right along, what we're looking at is James Paraffin Young. Paraffin is another hydrocarbon. A couple other hydrocarbons that are mentioned here are methanol or wood alcohol. Again, another hydrocarbon. And then the next one says, I'll just read from the book. A Scot, James Young, who was able to produce a superior illuminating oil of consistent quality using a process that he would recognize today as oil distillation and refining. So if you've ever driven past Billings, you'll see the great big refineries, these stills. And again, that's just a big hot stack, smaller, lighter molecules going to the top, heavier ones going to the bottom. That's basically what he's doing. He distills the paraffin, and now it just burns more consistently. This, in a very similar sense that you always put butane in your lighter, so the combustion is predictable. Okay. So moving from England over to the United States, the caption here says, Colonel Edwin Drake, foreground on the right, wearing a top hat, talking to an engineer in front of his oil well in Titusville, Pennsylvania. They struck oil at a depth of only 22 meters. Pretty impressive. Not quite as impressive as Jed Clampett of the Beverly Hillbillies, who struck oil at a couple inches in the movie, but 66 feet down, they're able to drill. And this thing's a gusher, right? So there's all that pressure of the soil and earth below it. It's kind of like popping a big zit. I mean, really. I mean, there's just oil, and out it comes. So very little investment. I mean, it's more difficult back in the day when you don't have access to some of the metallurgy and power equipment that we do to get to 22 meters. But the energy returned on energy invested is going to be quite high. So we talked about that a little bit in summary one. How much energy do you have to put in to get something out? And very nominal if you're only going to 22 meters in this case. That's also Titusville, Pennsylvania. If you remember, on the very first day of class, we did that 10 million to 1 ratio. That's kind of the date. And I think they mention right here 1859. I think the date that we selected was 1865 for that sort of, kick-started that Gaussian curve that we're right on the very top of right now. That's minute zero of that 2.5 minute carbon party we're in right now. Okay, I'm just turning over now to page 218. There's a title in here that says Petroleum for Transport. So you'll notice a lot of times these technologies will come in tandem, right? It's a chicken and the egg problem. You can think of the car as the chicken and the oil as the egg. You kind of have to have one with the other. But that's really a lot of times what happens in science and technology. One discovery sort of literally fuels another technology. Reading right here is coming down the line. International conflicts in the 1970s had a profound influence on global oil price and subsequent oil use. This is mentioned in box 7.2. I think we'll see that coming up here shortly. Oh, it's just right below it. Yep. Oil price shocks of 1973 and 1979. More or less what it was, different sovereign states in the Middle East had their own oil markets. And what they realized is if they were all sort of trying to undercut each other on prices, the price would stay low. But all of a sudden they said, guys, why are we fighting each other economically if we join forces and form a oil monopoly that's basically flowing from east to west across the Atlantic? we can cause an artificial shortage, increase the prices, and we're all going to get rich because the United States, more or less, in the mid-'70s, peaked. And we'll see a little bit more what that means later. But oil production on this continent, now it's happened a few times. There's actually a question later on in the book about when oil production peaked in North America. You might say, oh, it was 1940, it was 1970. Well, and these peaks occur with advances both in discovery and advances in technologies. But for all intents and purposes, oil production peaked in the continental U.S. in the mid-'70s, and that's when our demand for importing oil went up, and the major oil-producing countries in the Middle East sort of said, well, gosh, if we work together, we can make a heck of a lot more money. So that's what the artificial shortage was there. And that's basically the birth of OPEC. We talk a little bit, it says crude oil production grew to about 80 million barrels a day. In 2009, over 30% of the world's primary energy consumption. It says in the UK, in 2009, it was 1.6 barrels a day, around 1/3 of the country's primary energy needs. And, if you remember back to chapter 1 or 2, we know what primary energy is. It's energy that's coming, directly from the Earth's resources. Okay. They also mention figure 1.1. That was the very first figure in this book where they talked about world oil prices, and a lot of times the price is driven not by availability but by socio-political factors. In fact, I had a recent experience like that. I've mentioned this several times, where we put in a bid to do solar on the island of Antigua. It's in the Caribbean. It's got a population about the same size as Missoula, 65,000 people. They pay $1.25 per kilowatt hour for their electricity. We pay about 9 cents in Montana. Some of the highest prices in the continental U.S. are knocking on 20 cents a kilowatt hour. Hawaii can sometimes be as much as 25 cents. $1.25 a kilowatt hour. So there was an RFP, a request for proposal, sent out from the Antigua premier. Said, hey, why don't we put some solar panels up and bring the cost of electricity down? Well, at $5 a watt, we put in a bid to do a 1 megawatt array for $5 million. And at that rate, if you were selling electricity at that rate, you would make $20 million worth of electricity in 1 year. So for a $5 million investment now, for maybe a 6-month, 1-year project, you're going to get all of that money back every 3 months from now until forever.
400% return annually.
Yeah.
That's nuts.
Our response was no. It won't work down here. Sorry, it won't work. No other response than it just won't work. Well, comes to find out, we did a little bit of research, and in fact, the grid in Antigua is owned by a Syrian. And as it turns out, he also owns all the diesel shipping lanes in and out of Antigua. So there's no technological barrier there whatsoever. I mean, 5 megawatt or 1 megawatt arrays go up in Hawaii all the time. It's purely, as I mentioned, previously, political and social
So is that how
reasons.
they get their power from diesel?
Yeah. So they're burning diesel generators there to make electricity.
So he's just being greedy.
Right. Okay. So, and it's not secret. I mean, you can go out and read it on the Associated Press and all that. I just found it online. Okay, so we talked a little bit about oil. The next one there on page 219 is the natural gas industry, and there's two different, or several different ways to think about this. One is says natural gas is a rather different story to that of oil. It says, although associated gas is found with petroleum deposits, those are the figures we just saw, with the gas kind of floating to the top, sort of a natural distillation process. Natural gas can also be found on its own. This non-associated gas is believed to have its origin in fresh water rather than marine plant material. And so, have you guys driven by the landfill recently? I mean, there was the stack there that was burning the methane. That thing has been taken down. And I saw a bunch of guys walking around in hard hats a couple months ago. It looks like they might be putting up a new stack. I don't know if it was like an EPA standard they had to meet to make it cleaner burning, but that natural gas is the exhaust or the waste from anaerobic digestion. So microorganisms that are eating longer chain hydrocarbons is sort of poofing out that methane. So that's basically what they're saying here in the textbook is that the non-associated gas, the shales and things like that, different process, microorganisms more or less making that, those little tiny bubbles are trapped, and that's where a lot of this, kind of fracking stuff comes from, just going in, and knowing that those bubbles are there. It's not just like this nice big balloon of gas, but these little tiny bubbles, you go in there, just, blast the rock apart just with steam and heat, and then up the gas sort of coalesces and then comes back up. So slightly different, same molecule, CH4, it's just from a different origin. Okay, and then it says, like coal and oil, natural gas may be completely pure. Often associated gas is wet, and wells produce a mixture of natural gas, condensate, and natural gas liquids. Of course, and so these are longer chain hydrocarbons. One that's mentioned is pentane, another one is propane, et cetera, and so obviously these go off to a processing plant, they're distilled and purified and then sold as commodities. Okay, so that's just a little bit of background on where these materials are coming from. Now in terms of finding them, so you guys know the difference between sound waves and light waves. The sound waves are much, are slower, and they also propagate like so. So, I'm sort of sitting here, using my vocal cords, and the sound waves that, leave a source, like either vocal cords or the sonar that you see in the photo above, propagate in a spherical manner. So you hit a boom, the thing goes out equally in all directions until it hits something, and what the figure is depicting as well, it bounces off the boundary between two different materials with slightly different densities. And, the densities could be quite great in terms of, me yelling at the building across the street, and I'm going to hear that echo, the density between the air that the sound is traveling through, and it hits that wall and bounces back. The differences in densities could also be a little more subtle, where you just have two separate rock layers. But if you have something that's relatively impermeable, you're going to get the reflection just like you would off that building. So here comes the sound wave back, and now there are these, they just call them hydrophones instead of microphones. I mean, they're microphones sitting in the water, and they're set up in such a way that depending on what frequency is sent out, they can say, oh, this particular frequency penetrated to this depth, bounced off of here. I'm not going to pretend to explain the complexity, but there's a fair amount of mathematics going on in order to figure that out. It's not unlike the Doppler that you've probably seen if you've gone to the doctor's office or seen some of the ultrasound procedures where you're able to see inside of human tissue. Nevertheless, that's more or less what's going on, so that the people doing these explorations can then find these phase boundaries and then say, well, more than likely we've got a petroleum reserve down there. I don't know if you heard or not, but it sounds like, was it Shell that just kind of abandoned their Arctic exploration for the year? I mean, they were up there not too long ago, had some trouble, had to get rescued, and sounds like something similar. So kind of the more water you have to deal with, the tougher this is, and the more strata there are down there. So they took a chance, they took a gamble, and it looks like they had to retreat this year. Okay. Here's the next one. So once you've found something, the next step is to go after it and do some drilling. I had the neat little opportunity this past summer. The utilities were coming through and redoing some of the electrical lines in our neighborhood. And I don't think I ever really understood directional drilling until I got a chance to see the drill head on this thing. So what it is, if you've got, let's just say the drill, and you've all seen a regular drill bit that's helical or spiral and very symmetrical, just sort of drills straight. Well, the drill head on this directional drill, it was sort of bent in one direction. So it was constantly going to drill in a crooked direction. So the drill head was sort of, let's just say off to the left here, and there was sort of a shoe or a pad on the right, so which would basically act like a skid plate. So the thing was always going to go in some direction, but the operator could allow that drill head to either go, up or down, right or left. So he's got a sensor on the other end that tells him exactly where that thing is underground. So you can see now just expanding that to a larger scale. There's your directional drilling. It's like, oh gosh, how does this thing bend? Well, it's metal, it's long, it's just like a big drinking straw. You can think of it like a pole vaulter's pole. I mean, it's not going to do a 90-degree turn, but with the drill head technology, plumber snake. With the drill head technology, you can see how that would be achievable. And rather than having to set up 50 oil rigs for 50 holes, you can just sort of keep drilling multiple times. I even heard recently, this is kind of weird, but at the Montana Bureau of Economic Development not too long ago, some of the frackers were saying they can now drill up. So they drill down, they drill sideways, and now they're coming up.
Yeah, I didn't know
I didn't know that either.
They can go down in one place and shoot way over.
But once you're sort of horizontal, and like I said, if you've got that drill head that's
You just turn it up.
just turn it up. And so I'm kind of thinking, well, eventually they're going to come all the way up. They're going to hit the atmosphere and say, hey, there's a little bit of methane up here. Let's start sucking this down. So, it's just a little. I'm just wondering where is the limit? We've got the whole the whole planet's become this like Swiss cheese.
You could be really mean about directional drilling too, where you're drilling down close to the border of someone's property and then drilling down, accessing other people's property.
That's where mineral rights come into play.
That is a big concern. I think things have heated up in Texas a lot over that exact controversy as well. If we can't have access to your land by just coming in on the top, we'll get there some way. We'll just drill horizontally. It's and like any technology, it can be good or bad depending on your point of view.
They can't do that because if you own the mineral rights to your property, your property line goes below the surface, and those minerals,
belong to you. Yeah,
are yours.
Yeah.
They can't do it without paying for it.
Yeah. It's tough. I mean, you get into federal law, state law, etc. But let's do a few more, and then we'll take a break here in a couple of minutes. All right. So these are just different. These are different types of technologies, different strategies for getting to deeper petroleum reserves. So here's a wellhead, and I think we all remember hearing about the wellhead explosions there in the Gulf during that Deepwater Horizon incident. These things, of course, somewhere down here you've got your actual oil reserve, tremendous pressures, and just kind of going back to that popping a pimple analogy. If you tap that thing, now you've got the pressure, up comes squirting the petroleum products. So fixed platform at a relatively low depth, up to 500 meters, that becomes impractical once the water depth gets greater. Just imagine that whole thing having to get bigger and bigger. So you have a compliant tower, something that sort of can bend a little bit with the waves and the weather. Floating production, so again, highly impractical to get something that's actually attached to the seabed, so you've got something that's floating, and these guys just sort of allowing for a little bit of control around the outsides. This could be storage and offloading, so the ship itself could be mobile. Tension leg platform. Again, you're actually in every one of these cases you're having to get something secured down at the bottom of the
Basically, they
seabed.
just use a series of cables to basically make a.
Right, and so these two guys on the left are both what are called compression structures, where they're resisting gravity by pushing the thing up. The ones here that we see on the right are tension structures. So this thing is floating. The spar looks like it might be a combination of the two. But these things are all floating, thus allowing a much more nimble structure. We did something similar, kind of in reverse, a few years ago when we built a floating wind turbine. We were actually able to fill a balloon with hydrogen and float the wind turbine up. So rather than building a big wind tower, a platform with a lot of expensive materials, we just had 3 or 4 little guy wires and were able to build a floating wind turbine. So different strategies. Compression versus tension. Okay, so this is figure 7.7. It's called a McKelvey diagram, introduced back in chapter 5. Terminology in the oil and gas further splits reserves into 3 levels of confidence, as depicted here. So the proven reserves, the 1P or the P90 means that you've got a 90% probability that you're going to be able to economically recover these things. What's economically mean? It means you're going to put in $1 and you're going to get more than $1 back. You're going to put $1 into your research, your technologist, and that's going to come back to you as sales at the pump. The 2P, P50, it says it includes all the 1Ps with a medium overall probability of more than 50%. Well, how do you measure that? How do you gauge that? Well, because somebody sat down with all these numbers and sort of, based on what we saw previously in this other location with all the bouncing of the sonar, et cetera, we think we got a 50% chance of coming back solvent. So those are your 2Ps. And then proven, probable, and possible. So the probable of the P2 just means a 50-50 chance. And then the possible means that, it's might probably less than 50-50 based on the information that we previously have, but a low probability, over 10%. Okay. So, and then again, these are things that these conditional resources they will fall into one of these 3 categories. And then over here is just everything that's yet to find. When I did my professional engineering exam a couple of years ago, they actually did this same problem. They sort of said, we have consumed this much of the planet's hydrocarbons, how much are left? It was kind of a fun little exercise and some big numbers. Okay, 2 more sections and then we'll take a break, or 2 more figures and then we'll take a break, and then we'll get on to 7.5. All right, this is the oil spurting from the Spindletop gusher. This was in Texas in 1901, so 50 years or so after the discovery in Pennsylvania. Why did it happen in Texas after it happened in Pennsylvania? Well, there were just more people in Pennsylvania. There was nobody poking around in Texas up to that point. And what's kind of interesting too, it says in the figure, it says the pressure was actually used to drive the pumps. So you can kind of see that as a renewable energy resource to some point. I mean, obviously, once the pressure's gone, you can't drive the pumps. But they were sort of, rather than like, hey, let's send some electricity out there and build some pumps. No, let's just use that pressure gradient to pump the oil. Yeah.
Making the horse bail its own hay.
What's that?
Making the horse bail.
Oh, make the horse bail its own hay. And then here, traditional, the nodding donkey pump jack. So this is, accessing, once the initial gusher has dried up, the pump is here. This to me, we covered Watt's steam engine not too long ago, very reminiscent of this. This guy on the back side here is more or less your flywheel or your energy storage. And you can see that this nice curve here on the front is very similar to those curves we saw in Watt's steam engine, where you can take this rotational motion of the pump and turn it into this reciprocating motion to bring the oil up. And then one last thing, there are three different terms here mentioned. One is called primary recovery, and I'll read that. It says, once capped, once a gusher has been capped, the reservoir pressure can be used to drive the distribution, pumping the oil to storage tanks that may be tens or even hundreds of kilometers away, primary recovery. And then once the pressure has fallen, what you're doing is, it says various measures will need to be taken to extract the oil, such as raising it with pumps or injecting it with water or gas or something other. Now they're using CO2 in some cases for secondary recovery. It says primary and secondary recovery typically succeed in 30 to 50% of the oil. And then finally, tertiary oil recovery refers to the extreme techniques of injecting steam, CO2 like I just mentioned, or nitrogen. So, it's sending a gas down there to displace the oil and bring it up that way. This typically allows a further 5 to 15% to be extracted.
You never really go above 65%.
You don't, and on that note, and a lot of times we don't really fully appreciate the physics or the economics of that, but if you don't mind, I'm just going to show you once again that Schramsky paper, because the figures that we've just seen are brought to bear quite a bit in that Schramsky paper. So let's just take a look at that quickly. Yeah, so here's this 40. See, this is your recoverable fossil fuel potential. That is more or less this box, the entire box, 40 zetajoules. Now, and again, remember that Schramsky is talking about oil, coal, natural gas, and even uranium, non-renewable primary energy sources that are buried beneath the ground. 2,000 not recoverable. So we're just talking about what's recoverable from these conventional oil wells. That's carbon that's like in beach sand or at the bottom of the ocean, and like little flecks that fall down that a shrimp doesn't happen to eat on the way down. I mean, it's there, but in terms of economic recovery, forget about it. It's not, at least with conventional means. So, okay, let's take a break there.